Hey guys, welcome. Yeah, so I hope everyone is doing well, and I've already shared 2 review videos for the 2020 AP Calculus BC exam coming up soon. And although I did not intend to make this video, I found 3 really interesting questions that are not represented in the previous 2 videos, and so I thought these would benefit everyone, and so here goes. And in all 3 of them, I cite my source. So this first question is from the 2013 BC FRQ, and it's problem 6 there. Okay, so take a second to read it, and then let's get started. Now, in part A, it says, it's known that f of 0 is -4, and the first degree Taylor polynomial centered at 0, and therefore the Maclaurin, when evaluated at 1/2, gives the number -3. So the value of the first degree Taylor when we plug in 1/2 for x is -3. Again, it's centered at 0, and therefore it's a Maclaurin series. And so what we have to do is show that f prime of 0 is equal to 2. Now, the first degree Taylor centered at 0, we know is going to be f of 0, and then plus f prime of 0. If you're not following, this is part A, right? And then it's x, otherwise over 1 factorial, and it's x to the first. And so this is, in general, for any function, right? Any function f, this is in general p1 of x, right? Okay, now, we know that p1 of 1/2 is equal to -3. We're also told that f of 0 for this function is -4. So we see that what we have is saying that this translates to -4 plus f prime of 0 times x is equal to p1 of x. And then, since x is 1/2, so 1/2 is plugged in for x, we see that this is going to turn out to be -4 plus f prime of 0, and then x is 1/2, as I just said, times 1/2 is going to equal p1 of 1/2, which is -3, so it's going to equal -3. And what we have to show is f prime of 0 is 2 from this equation, and that's pretty straightforward. It's like arithmetic that you have left to do. If you want to call it algebra, you can call it that. So we've got f prime of 0 times 1/2 is equal to -3 plus 4, right? Adding 4 to both sides of this equation. So that would read 1, multiplying both sides of this by 2. We see that f prime of 0 is equal to 2, right? Yeah? Okay, cool. So this is very straightforward, although it's quite unique the way in which it's asked. And yeah. All right. And so what's next? Next is part B. So part B says it's known that f double prime of 0 is that, and f triple prime, and so we have to find the third degree Taylor centered at 0. Now the third degree Taylor centered at 0, p3 of x, is f of 0 plus, we already saw the first 2 terms from the first degree we just discussed, and then this is x, and then plus f double prime of 0 over 2 factorial, and then it's x squared plus f triple prime, and I'll just write that for triple prime of 0. It's typical to do that, over 3 factorial, right? And then it's x cubed. Okay, cool. So f of 0 we already know is -4. F prime of 0 we had to show was 2 in the first part, so we've got plus 2x as the second term, and then plus f double prime of 0 we're given, so it's actually minus, and it's -2/3, right? Okay. And then over 2 factorial, so the denominator actually turns into 6, but then that's going to turn out to be -1/3, so let's write -1/3, and then it's otherwise x squared, okay? And then plus f triple prime of 0 is 1/3, but then we have to divide by 3 factorial, which is 6, and this is positive, so it's really 1 over 3 times 6 is what we're going to get in the denominator, so that's 18, and otherwise we've got x cubed. And so I simplified and yada yada, and so this is an efficient way to answer part B. Okay, so then part C. Okay, part C says the function h has first derivative given by h prime of x is equal to f of 2x. H of 0 is 7, and we have to find the third degree Taylor for h. So, okay, we just did the third degree Taylor, but for f, and so for h, it's going to look very similar, only it's going to read h of 0, right, plus h prime of 0x, and then plus h double prime of 0 over 2 factorial times x squared, and then plus h triple prime of 0 over 3 factorial times x cubed, right? Okay, cool. So it's clear that since we're only given h of 0 and just h prime, we need to work a little bit to find h double prime and then h triple prime and plug in 0 into them, right? Okay, so h double prime of x is going to be equal to the derivative of, so d dx of h prime, right? Okay, cool. Now, h prime is right here, so we're saying d dx, the derivative of f of 2x, right? Okay, cool. And now, so then we see that h double prime is going to equal, the derivative of this, which is going to say f prime of 2x, and then by chain rule times 2. Got it. And for h triple prime, where do we have space? So h triple prime of x is going to be the derivative of the second derivative of h, right? It's the derivative of h double prime, and so it's the derivative of this. So what is that going to say? That's going to say 2 times f double prime of 2x, and then again by chain rule times 2, so that is 4 times f double prime of 2x. All right, got it. So then we see that the third degree Maclaurin, or Taylor centered at 0, for h is going to be, well, we're given h of 0, as I said, that's 7. So 7, and then plus h prime of 0. H prime of 0 is, since h prime of x is this, it's going to be f of 2 times 0. So that's f of 0, right? And so we were given f of 0 somewhere, and that's -4, right? So we're going to have f of 0, which is -4, so -4, and then times x. So I'm saying h prime of 0 is going to simply be f of 0. Just plug in 0 here, which means you plug in 0 here, that turns into f of 0. And we're given f of 0 right here. So we've got -4x plus, and then h double prime of 0, we labored hard to find. It's right here. And that was 2 times f prime of 2x. So h double prime of 0 is going to be 2 times f prime of 2 times 0, but that's just 0. So it's just 2 times f prime of 0. Now f prime of 0, as we found in part A, was 2. So we're going to get 4 here, right? Okay, so we've got plus 4, but then we have over 2 factorial, and then x squared, right? Okay, cool. Plus h triple prime of 0. So since h triple prime is right there, we see that h triple prime of 0 is going to be, I suppose I'll do it in black. H triple prime of 0 is going to equal 4 times f double prime of 0, right? Remember, h triple prime we found was that. And obviously 2 times 0 is still 0. Okay, f double prime of 0 we're given over here. That's -2/3. So what we have is h triple prime of 0 is going to be 4 times -2/3. And so that's going to say -8/3, right? Okay, cool. And so it's actually negative, so I shouldn't write plus. It's going to be -8/3, but then we're dividing by 3 factorial. So we're going to have 6, which is 3 factorial times 3. So that's 8/18, and then x cubed. Obviously, there's a little bit of simplifying you could do in this part and this part. I'll leave that to you, but we've answered the question now. Yeah? Okay, cool. So on to the next one then. And the next one is this. This is a really cool question. It's probably my favorite of the 3. And this comes from the 2013 BC FRQ, and it's problem 5 there. All right, cool. So read it. We've got a shaded region here. And so the first thing we've got to do is find the area of the shaded region. This is pretty straightforward. Top function minus bottom function inside of the integral. but otherwise from 0 to 1, we don't have to find the limits. It's pretty obvious to find that the bounds are along x, and they go from 0 to 1. So 0 to 1, and top function minus bottom function. The top function is what's given here, and let's actually call it f of x, and then this let's call g of x, as we're going to refer to them quite a bit in this part. So 0 to 1, f minus g dx, right? Okay, so that's f is x e to the x squared, and then minus g is minus 2x, so it's actually going to be plus 2x at the tail end, right? So plus 2x, and then dx. Now, finishing this integral is a very straightforward task. This part will involve a little bit of u sub, just make u x squared, and otherwise you should know how to integrate this. And so I'm not going to finish it. I'll let you do that. Part B. Part B says, Part B says, write but do not evaluate an integral expression that gives the volume of the solid volume when generated Part B says, write but do not evaluate an integral expression that gives the volume of the solid generated when this region is rotated about the horizontal line y equals -2. Now, notice that the horizontal line y equals -2 is going to look exactly like this, which is it's going to catch the shaded region right there. It's going to intersect it right at that corner. How do I know that? Well, because this bottom function, this linear function, is g of x, which is minus 2x, and if we plug a 1 into it, we see that the y value here is going to be -2. So figure not drawn to scale, because this here is 1 and this is -2. Wait, no, right? But anyway, we figured it out. Now, anytime you have to do volume, right, we know that it's either disk, or it's washer, or it's shell, or it's cross-section. Right? Okay. And here, since there's a gap between the axis of rotation and the region, we know it's going to be washer. You should know when to use shell, and disk is when there's no gap between the axis of rotation and the region. And cross sections, I'll just briefly mention, is just a of x dx, and they'd have to tell you or say the phrase cross section, right? Because they'll tell you what the cross-section has to look like. So for example, if the cross-section is semicircular, it would look like this. And so you see that the diameter of the semicircle is the top function minus the bottom function. You have to divide that by 2 to find the radius. And then otherwise, you have to do pi r squared divided by 2, because it's a semicircle integral of that. So integral from 0 to 1 of pi r squared divided by 2, where again, r is this top function minus the bottom function divided by 2, right? Okay, and again, you do pi r squared divided by 2 because it's a semicircle. Otherwise, it's straightforward. I wanted to mention this, as I am trying to help you review. And otherwise, we've, in this problem, identified that what we have to do is the washer method. And so let's get on with the washer method. As soon as you figure out which of them it is, right? The first thing you should do is just write the formula. So for washer, we know it's going to be pi, and then integral big R squared minus little r squared. And then if you're rotating about a horizontal axis, it doesn't matter where it is, it's always going to be dx, right? And so the task is, let's figure out what big R and little r are. Okay, and to that end, what you should do is draw a vertical line from the axis of rotation until you encounter one of the functions. And so that's going to be little r, the first function you encounter when you draw a vertical line from the axis of rotation to the region, right? So that bit is little r. So we see that little r in this case is the function that is g, so that's minus 2x. Okay, and then do the same, which is draw a vertical line, this time until you encounter the second function, and that's big R. So we see that here. is going to be, well, it's a little bit of thinking for big R. Because notice that this little bit from the x-axis here, that's f of x. But then we have this whole distance from here to here, and it's a constant value, this vertical distance, regardless of where I draw it, and that's a constant value of 2, because we know that this here is -2, this y value, but then since it's distance, we have to take it to be +2. So we see that big R in this case is going to be, big R is going to be +2. That's this vertical distance, right? This vertical distance plus this little bit, and this little bit is the value of f at whatever x this is, right? So it's +2 plus f of x, and f of x again is x e to the minus x squared. Okay, so thank goodness, thank Jesus that we don't have to actually do this integral, we just have to set it up. But otherwise, you know, a to b here I'll write, but we know that those limits are 0 and 1. And big R is 2 plus x e to the, is it? No, there's no minus on this part, it's just x squared. My bad. Okay, so x e to the x squared, but then squared, this is big R, so squared, minus little r, which is -2x squared, and so -2x squared. I was going to write just +2x. Well, since we're squaring it, it won't matter if it's -2x or +2x, but you know, I want to keep consistent with what we've named g, or the given function g, and so yeah. All right, so we just throw a dx here, and so if you write this, you should get full marks for this part. All right, so what is next? This last bit is very atypical. I have looked at a lot of FRQs over the years, right? And I have never seen one where you have to do a line integral, and that's what we have to do for part C. We have to do a line integral. Why? Because it says, write but do not evaluate an expression involving one or more integrals that gives the perimeter of R. So we need to know the perimeter of R, so the length all the way around. All right, now, although they say you can use more than one integral, I'll show you a trick that will allow you to only write one integral. And that's because we know that on this end of the perimeter, right, like from here to here, we already said is 2. From here to here is the value of f at x equals 1. So what I just said is this little bit is 2, and this little bit is f of 1, where again, f is this function. So if we plug in 1 into here, we're going to get 1 e to the 1 squared, and that's just e. So this little bit is e. And then we've got from here to here, right? From here to here is the hypotenuse of a right triangle. If you don't know what right triangle I'm talking about, I'll close it off right there. So there's a right triangle right here, right? And for this right triangle, again, one leg is 2, and figure not drawn to scale again, this little bit is 1, because that's 1 right there. And so if you do Pythagorean theorem, you see that 1 squared plus 2 squared has to equal this squared, and so this means that this is square root of 5. So far, our running total for the perimeter is 2, so this is part C. We've got 2 plus e plus root 5, and root 5, this is just me showing off, I've committed to memory, is approximately 2.23, and then of course we have to do plus the length of this curve, right? And this is where a line integral is involved. I'll do this in black. Now, real quick, a line integral is always the integral of ds, where ds is going to equal one of two things. It's going to equal the square root of, annoyingly, I'm going to write a square root with a ruler, because, yeah, I'm annoying and a neat freak. So ds is going to be 1 plus dy dx. I have videos dedicated to line integrals, so you can check those out. And then don't forget, outside of the square root is dx, so long as the function is y equals f of x. In other words, y is a function of x. And let's say that the x is going to range from a to b, and just to distinguish the range of the y's, let's say that the y range is c to d, and this time we're given x is a function of y, so let's say x is g of y, then this time ds is going to look as follows. ds this time will be the square root of, you can take a wild guess as to what we have to write. It's going to be the square root of, this time it's going to be 1 plus dx dy squared, and then dy outside. Yeah, okay, so you see the expression for ds is going to depend on whether or not the function is y equals f of x, or of this form, so y is in terms of x, or x is in terms of y, right? Okay, so clearly here, what we're given is y is a function of x, so we're going to use the first of the two ds formulas we've written down, and a and b clearly are along x, and they're 0 and 1, so the task is simplified here. So if we do this in red, right, so what we have to add to this to figure out the length of that is 0 to 1, and then ds is the square root of what? The square root of, I don't know if I could fit all of this junk in there, but we'll figure it out. Square root of 1 plus, and then dy dx. Well, if this is y, dy dx, notice is going to be the derivative y prime, so that's dy dx, and it's going to involve that we do product rule, because there's a product between x and e to the x squared, so the product rule, remember, is f prime g plus f g prime, where this time f is x and g is e to the x squared. So abandon the fact that we called this whole thing f and this whole thing g. Shouldn't be confused by that, but just in case. So, and you should also know the product rule. You shouldn't need reminding from me. Anyway, f prime is 1. That's the derivative of x, and then times g, e to the x squared, plus f, which is x, the derivative of g, the derivative of e to the x squared, that's 2x e to the x squared, right? Okay, cool. So if we clean that up, right, and where could I write? I'll write up here. If we clean this up, it's going to say, well, I can factor on e to the x squared because it's both in this term and this term. And once I do, what I could write is e to the x squared, and then 1 plus, and these guys are going to combine to 2x squared. 2x squared, got it. And we have to square all of this because it says dy dx squared inside the square root. All right, we got it. Thank goodness, thank Jesus that we don't have to actually do this, but do the integral, but it's 1 plus 2x squared. Again, this is very atypical. I don't remember another FRQ question where you have to do a line integral. But, you know, this is why I picked these set of questions to discuss with you. Okay, this is it. All right, so that completes this problem in its entirety. And I believe we've got one more to cover before we say we are done in this video. Yeah? All right, let's get at it. Okay, so the last of the bunch is this problem, and this is from the 2013 BC FRQ also, and it's problem 5. And this is nice and sweet and short and straightforward, yeah? Okay, cool. And yeah, so first thing is we have to evaluate this limit. Notice that f prime, or dy dx, is given here. And we also know f of 0 is equal to -1. Make sure you read the questions carefully. Yeah, okay, all right. So then on A, right, so the limit is x goes to 0 of this quotient is going to be, I don't even know why I'm rewriting the question, but it's fine, it won't hurt, sine x, right? This is going to equal, so you know that we're doing part A, I suppose, f of 0 plus 1 over sine of 0. Ah, surprise, surprise. Okay, so since f of 0 is -1, we see that it's -1 plus 1 over sine of 0 is 0, so this is 0 over 0. And therefore, we have to use Bernoulli's rule. Yes, you heard me right. I called it Bernoulli's rule because, well, it's Bernoulli who came up with it, although L'Hôpital paid for it and got credit for it. And so if we use Bernoulli's rule, what we're going to find is that this will have to equal, right? This limit will have to equal the same as x going to 0, the derivative of the numerator, that's just f prime of x, and then divided by the derivative of the denominator. The derivative of sine is cosine, so cos x. Now we know it's going to work out because regardless of what the numerator is, cosine of 0 is 1. And the numerator is f prime of 0, right? And since f prime is dy dx, we have to plug in 0 into this. Notice that this expression requires that we know both x and y coordinates at 0, and we do. F of 0 is equal to -1 means that the point 0, -1 is on f, and so we will be able to plug in 0 for x and dy dx, and then -1 for y, so we can figure out what f prime of 0 is. But yeah, in execution, we're saying f prime of 0 divided by cosine of 0. Again, cosine of 0 is 1. And so f prime of 0 is going to equal, as I said, dy dx evaluated at 0, -1. And so that would be -1 squared, and then times 2 times 0 plus 2. And -1 squared is 1 last time I checked. And this inside is going to turn out to be 2. So we see that we're going to get 2 over 1, or simply 2. Cool. So part A is done. Part A. Okay. All right. So next is Euler's method. Now, I shared a previous video recently on Euler's method where I used an APFRQ as my basis or my example. And so, you can't expect the same level of detailed discussion in this video, but we'll do it because it says to do it in this part. Why not give you like another example? I had a while back shared a thorough discussion on Euler's method, so by the time we're done with part B, you'll have 3 versions of Euler's method from me. Okay, cool. Use Euler's method starting at x equals 0 with 2 equal steps, or 2 step sizes with 2 steps of equal size. Well, step sizes of equal length to approximate f of 1/2. All right, so as I've said in that video dedicated to Euler's method, if you have 2 step sizes, then you're going to need 2 tangent lines. And I named them T1 and T2, so let's do the same, T1 and T2. T1, the first tangent line, is going to be at the first point, at the starting point. So that's at 0, comma, what's the y value? Well, since f of 0 is -1, it's 0, comma, -1. Okay, remember, it's best to write the equation of a line to start in point slope form. That's y minus y1 is equal to m times x minus x1, right? Okay, so we've got our point x1, y1, that's 0, -1, but we need m, the slope. So that's dy dx evaluated at 0, -1. Hadn't we already done that? So if we just do it quickly again, that's going to be -1 squared and then -1 squared times 2 times 0 plus 2. So that's 1 times 2. So dy dx is 2. So we see that T1 is going to be y minus -1 equals m, which I just said is dy dx evaluated at 0, -1, and that's 2 times x minus 0. So this is going to say y plus 1 is equal to 2x, from which we see that in slope-intercept form, y is going to be 2x minus 1. Now, we use T1 to find the corresponding y value to the next x using our step size. Since we're going from x equals 0 to x equals 1/2, since we want to approximate f of 1/2, and the middle where we're going to step is x equals 1/4, right? Okay, so then we've got our second x for T2, it's 1/4. The x's are always easy to find, just count by how many step sizes you're using, right? But the y, we're going to use T1 to approximate the y value at x equals 1/4, since we don't know f. And so then the y value at x equals 1/4 is going to be, this is going to be T1 of 1/4, right? And so if I may use a very cumbersome expression, that's going to be 1/4, comma, if we plug a 1/4 in here, what are we going to get? 2 times 1/4 and then minus 1, right? So that's going to be 2/4 or 1/2 minus 1, which is going to be -1/2, right? Okay, so -1/2 here then, right? We didn't do anything wrong, did I? Okay, just very quickly double checking. So y minus -1, that's y plus 1, and then 2 times x minus 0, that's right. So yeah, that's good, that's good. All right, that's good, yeah. And 2 times 1/4 is 1/2. Okay, yeah, okay, we're good. All right, so then we've got our point, but then we need the slope for T2, right? And the slope for T2 is going to be dy dx evaluated at this new set of points, and that's 1/4, comma, -1/2. And so what's that? That's going to be -1/2 squared, and then times 2 times 1/4 plus 2, right? And so that's going to be negative a half squared is 1/4. And then we're going to get, what is this? 1/2 plus 2. What's that? That's 5/4, right? No. 1/2 plus 2 is 5/2, right? Okay, my bad. Isn't that? Yeah, so that's 1/2. My arithmetic is terrible, guys. 1/2 plus 2. And so that's 1/2 plus 4/2. And so that's 5/2. Yeah, I'm right. Okay. All right. So that's 5/8, right? Okay. So then we see the T2 is going to be y minus, and then the y value is negative 1/2. So really, plus 1/2 equals, and then the slope is 5/8. So 5/8, and then x minus 1/4, right? Okay, cool. And so then isolate y here. So y is going to be 5/8, and then x minus 1/4, and then minus 1/2. Okay, so since this is T2, just plug in 1/2 in here, and that's going to be our approximation of f of 1/2. Yeah? Okay, cool. Again, other than not being good at arithmetic, I don't enjoy it. So I've taught you everything you need. You can plug in 1/2 for x there to figure out f of 1/2 approximately. So I'll let you do that. All right, to conclude, we need to find the particular solution to this differential equation. And although there's a whole course called differential equation where you learn lots of techniques for solving differential equations. By the way, I have lots of videos on differential equations. Check them out. The only technique that you've learned in Calc BC is separation of variables. So do that. So if in this differential equation you separate the variables, what you have to do is divide by y squared, and then on both sides, and then multiply by dx. And if you do that, then you're going to write 1 over y squared dy is equal to, and then it's 2x plus 2 times dx, right? So we are done separating the variables. But then the left side, you should probably write as y to the negative 2 dy, so that it's friendlier to take the integral of, because, well, our next task is to integrate. And you don't have to factor out this 2, but you can. I want to. And then, so, yeah. Okay. So then the next thing we're going to do is throw an integral sign here, throw an integral sign here. And so we integrate both sides. When we do, this is going to be y to the negative 1 divided by negative 1. So that's negative 1 over y, and then plus c. But we're going to combine the c from the left and the c from the right and write 1c on the right-hand side. And so, you know, we could write this 2 in front of the integral. So you've got 2 times the integral of x plus 1, and so that's x squared over 2 plus x, right? Okay, maybe it was too like interesting a path, too scenic a path for me to have factored out that 2. Should have just kept it right where it's at. And anyway, so we see that like negative 1 over y, right, is going to be equal to, well, we can cancel these 2, so that's going to be x squared, and then plus 2x, and then plus c, right? Okay, cool. Now, use this trick instead of cross-multiplying or whatever algebra you're going to do, which is write both the left and the right side as like quotients, right? And exploit the fact that like if like a over b, right? If a over b is equal to c over d, then it follows that b over a has to equal d over c. So exploiting this fact, which is flip both sides, you're going to write that this implies that negative y over 1, or negative y, is equal to 1 divided by, and then it's 1 divided by what? 1 divided by x squared plus 2x plus c, right? And so multiply both sides by negative 1, and so you're going to get y is equal to 1 divided by, 1 divided by, I see that I'm not practicing what I usually preach, which is it's almost always, and this is negative since I multiplied on this part by negative 1, my bad. So it's almost always best to find c at the earlier step after integrating both sides. What did we have after integrating both sides? We just had this here, right? And so I'm saying as soon as you finish integrating both sides and you write a plus c on the right-hand side, that's the time you should figure out what c is. We could do it here at the end, but again, I always advise that you find c as soon as you're done integrating both sides and you write a plus c on the right end. How are we going to find c? Well, using the initial value that when x is 0, y is -1. So that means that this is going to say -1, y is -1 over -1 is equal to, right? Y is -1 right there. Make x 0, so 0 plus 2 times 0 plus c. See, I told you, finding c here is easier, so c is 1. So in conclusion, we replace this c with 1, and we see that we are done. Ah, that rhymed. Okay. I hope you found this like interesting, beneficial, and all that good stuff. Yeah, all right. I hope your prep is going well, and good luck. There will be one more video from me, so look out for that. Otherwise, take care.